Hello and welcome back to Higher Maths Differentiation. We're looking at graphs of derivatives. The derivative of an x to the n term is an x to the n minus 1 term. The power lowers by 1. For example, if we find the derivative of a cubic, where x cubed is the highest power, that will be a quadratic, where x squared is the highest power. So if we differentiate an x cubed, we'll get 3x squared, for example. So we've gone from a cubic to a quadratic. When drawing a derived graph, all stationary points of the original curve, I'll tell you what, we'll come back up to this in a minute. We'll look at some examples first of all. Right, the derived graphs are underneath here. These graphs describe the gradient on these original graphs. So for this value of x here, so here, the gradient takes a negative value. So on the original graph, the gradient for this value of x was negative. When x is 0, the gradient on the original graph would be negative. It was going down. When x takes this value here, whatever this value of x is, looking up, we're getting a positive value. Remember, this graph describes the gradient of the original graph. So on the original graph, if we go straight up, it should be positive. It is. This point here has a value of 0. So whatever x coordinate that is, the value is 0. It's not a negative or a positive. It's sitting on the x-axis. It's 0. So on the original graph, that should have a gradient of 0, which it does because it's a turning point. Gradient 0, it's flat at that point. Let's have a look at it with a cubic. So remember, if we differentiate a cubic, we'll get a quadratic. So that's how we know what kind of curve we should be looking for. So here, this is increasing. So on the graph below, the curve should be above the x-axis, because for any value of x left of this first root, that says on the original curve, there should be a positive gradient, which there is. Now this turning point has a gradient of 0, so that would have to be sitting on the x-axis. This turning point has a gradient of 0, so that would also be sitting on the x-axis. In between, we have a decreasing gradient, a negative gradient. So on the original curve, we have a negative gradient. So on the graph that describes the gradient, that must take a negative value. So here we have a value of possibly negative 1/2, then maybe negative 1, then maybe negative down as far as negative 2. Now this starts to increase again, but this still has a negative value at this point. This is still a negative value here. This might still be negative 1, then negative 1/2, then negative 1/4, then negative 0.1, until it gets back to 0, which is this turning point. So wherever this is decreasing, this must be below the x-axis. And again, afterwards it's increasing, so it needs to be above the x-axis here. So that is what this part means. So all stationary points of the original curve become roots. Stationary point will be a root on the graph of the derivative. Wherever the curve is strictly decreasing, in other words going down, it has a negative gradient, the derivative is negative, so the graph of the derivative will lie below the x-axis. So here the curve is strictly decreasing, it has a negative gradient. So for that section of the graph, on the graph of the gradient, the graph of the derivative, this must lie below the x-axis. Wherever the curve is strictly increasing, the graph of the gradient or the graph of the derivative must be above the x-axis. So let's just match that up on the final one as well. So it's an increasing gradient, so we're looking above. Then we're decreasing, so it's below. Then between these 2 points, it's increasing again, so it comes up above. Then finally it's decreasing, so it's a negative gradient. So on the graph of the gradient, the graph of the derivative, it should be falling. It should be below the x-axis, which it is. Okay, right, I've got a couple of examples to do underneath, which I'll do in a separate video. This is a topic where it's either, yep, get that, or it can be a little bit of a struggle, but the penny will drop if you put in enough work on it, guys. So please do.